In the quiet darkness between galaxies, something stirs. A flash, a ripple, a heartbeat of impossible energy. Astronomers call it a cosmic tipping point, the moment when nature itself, pushed to its limits, seems to snap. Across the universe, these moments play out in silence. A star's magnetic field twists upon itself and lashes outward as a solar flare, hurling radiation across the void. A dying giant begins to fuse iron, the last act before it detonates into a hypernova bright enough to outshine its entire galaxy. And deep within the frozen stillness of space, a dead star spins faster and faster, until its crust cracks open with the force of 1 billion atomic bombs, releasing a burst of gamma rays that can sterilize worlds. Each of these events is a warning sign. The universe is not as stable as it looks. It lives on a knife's edge, a delicate balance between creation and destruction. Push too far, and even the laws of physics begin to tremble. For centuries, we've comforted ourselves with the illusion of permanence, that stars will always shine, that space will always be still, that reality itself is built on unbreakable rules. But the more we look, the more those rules seem to bend. What happens when they finally break? This is the story of what lies beyond that edge, of stars so dense that a teaspoon of their matter outweighs a mountain, of forces so extreme that atoms collapse, electrons vanish, and neutrons fuse into something stranger still. And of the scientists who've spent a century trying to understand how far the universe can be pushed before it falls apart. Our journey begins not with a telescope, but with a question, one that has haunted astronomers since the first time they saw a supernova flare in the night sky. What happens to a star when it dies and refuses to disappear? The answer takes us to the very boundary of physics, to the invisible border between existence and annihilation. Somewhere out there, in the darkness between galaxies, are objects that should not exist. Neutron stars, quark stars, maybe even something beyond both. Forms of matter so compressed that our equations break down and our understanding dissolves into speculation. They are the universe's paradoxes, tiny, invisible, but unimaginably powerful. A neutron star packs the mass of our sun into a sphere barely 20 kilometers wide. Its gravity crushes atoms into nuclear paste. Its magnetic field could strip data from a hard drive on Earth from halfway across the galaxy. And its surface, smooth as polished metal, burning at millions of degrees, marks the boundary between order and oblivion. For decades, these stars have been the ultimate physics experiment, laboratories that no human could ever build. They test the limits of Einstein's relativity, quantum mechanics, and even our most sacred equations of state, the mathematical scaffolding that keeps reality from collapsing in on itself. But what if some of them have already gone too far? In recent years, astronomers have begun to find neutron stars that shouldn't exist, stars heavier than theory allows, stars that refuse to collapse into black holes. Among them is one that has become the center of an astronomical mystery. J0740 plus 6620, a neutron star so massive and yet so large that it defies every known model of stellar physics. If the equations are right, it shouldn't be there. And if it is, something fundamental about the universe must be wrong. To understand why, we'll have to journey from the surface of our own sun to the cores of dying giants, through the violent birth of neutron stars and into their impossible interiors, places where gravity, quantum mechanics, and nuclear physics collide. We'll follow the scientists who uncovered their secrets, from colonial India to wartime Cambridge, from the icy silence of space stations to the laser detectors that measure ripples in spacetime itself. Because in the end, this story isn't just about stars. It's about us, about the limits of our understanding, and the thin line between the laws we know and the chaos waiting beyond them. So, what really happens when the universe reaches its breaking point? When matter is crushed beyond recognition, and the very fabric of reality begins to tear? Let's find out. Part 1. The first signs. A star that shouldn't exist. In the spring of 2021, an unexpected signal arrived at NASA's Goddard Space Flight Center. It came not from a distant galaxy or an alien probe, but from a small, box-shaped instrument bolted to the outside of the International Space Station. Its name was NICER, the Neutron Star Interior Composition Explorer. For nearly 4 years, NICER had quietly watched the universe in X-rays, mapping pulsars, dead stars spinning hundreds of times per second. But that morning, as engineers began parsing through its latest data dump, something stood out. A neutron star, catalogued simply as J0740 plus 6620, was sending back measurements that made no sense. At first, the numbers seemed wrong. Impossible even. The star's mass appeared to be too large, more than 2 times the mass of the Sun, yet compressed into a sphere barely 20 kilometers wide. According to decades of physics, that shouldn't be possible. When astronomers double-checked the signal, the data didn't budge. Every pulse, every fluctuation in X-ray brightness confirmed it. The equations of state, the delicate mathematical relationships describing pressure, temperature, and density inside a neutron star, could not explain this object's size. The universe had, once again, overstepped its own boundaries. To the untrained eye, J0740 plus 6620 looked like any other pulsar, a pinprick of light buried in a sea of stars. But for astrophysicists, it was an omen. If the numbers held true, then the laws governing the behavior of matter at nuclear densities, laws built over a century of research, might need rewriting. It wasn't the first time a star had done this. The history of astrophysics is littered with celestial rebels, objects that refused to fit neatly into theory. The Sun itself once defied understanding. In the early 1900s, scientists could calculate how much energy it emitted, but they had no idea how it produced it. Chemical combustion and gravitational collapse couldn't possibly sustain billions of years of light. The mystery wasn't solved until a young Indian physicist named Meghnad Saha proposed a revolutionary idea: that the behavior of atoms inside stars could be predicted using ionization equations, a bridge between heat, pressure, and the charge of matter. That discovery changed everything. For the first time, astronomers could map what stars were made of, not just their brightness, but their chemistry. Saha's equation laid the foundation for understanding stellar structure. A century later, that same logic, the interplay between pressure and temperature, remains at the heart of the equations of state used to describe neutron stars. But where Saha's equation worked beautifully for ordinary stars, it begins to crumble in the face of something as extreme as J0740. At such densities, atoms are stripped of their electrons, crushed into a nuclear soup. Neutrons press against one another with a ferocity no laboratory on Earth can reproduce. Quantum mechanics, that strange, elegant system of rules that governs the subatomic world, becomes the only thing standing between matter and total collapse. And yet, even quantum mechanics seems to waver here. When news of J0740's properties began to circulate through the astronomical community, the reactions were a mix of awe and disbelief. Some researchers dismissed the early measurements as calibration errors. Others suggested the neutron star might be distorted by rotation, appearing larger than it truly was. But as the data improved, these explanations fell away. There it was, a neutron star heavier than theory allowed, and still somehow resisting collapse into a black hole. Something inside it must be fighting gravity harder than expected. A new kind of pressure, a new form of matter, or perhaps an entirely new phase of physics. For decades, neutron stars have been considered the final step before oblivion, the last bastion where quantum rules can still hold gravity at bay. Push them any further, and the result should be a black hole, a place where spacetime folds in on itself. But J0740 refuses to obey. The object became a cosmic paradox, massive but stable, compact but stubbornly large. Its very existence hints at new forms of matter lurking within its core, beyond anything known. Perhaps quark matter, a soup of subatomic particles freed from the confines of protons and neutrons. Or maybe something even stranger, a Bose-Einstein condensate star, where matter moves as a single quantum entity, defying gravity with collective precision. Each theory sounds more like science fiction than science. And yet, each one might hold the key to understanding why the universe hasn't yet torn itself apart. For the scientists at NASA and their colleagues around the world, J0740 became an obsession. They pointed every available telescope toward it. Radio observatories timed its pulses to the millisecond. X-ray satellites mapped its surface. If the data could be trusted, then the neutron star's strange dimensions could narrow down the true equation of state and reveal once and for all how far matter can be pushed before even physics breaks. But the further they looked, the stranger it became. Its pulses were unusually sharp, its rotation surprisingly stable, its emission spectrum inconsistent with any known model of neutron star crusts. Even its size, measured by how light bent around it, defied prediction. The more the data piled up, the more the star seemed to whisper, "You don't know me yet." In the quiet control rooms of NASA and the European Space Agency, whispers turned into questions. Could the star's interior be made of something other than neutrons? Could dark matter, the invisible mass that holds galaxies together, be hiding inside, changing its structure? Or was this the first glimpse of a new kind of star, one that existed only in the gray zone between reality and impossibility? The hunt for answers would soon draw scientists back through time, to the first theories of how stars die, to the war-torn laboratories of early 20th century Europe, and to a series of discoveries that would change our understanding of the universe forever. Because before we can understand what J0740 is, we must understand how stars break, and what stops them from breaking completely. Part 2: The Collapse. When stars die and refuse to disappear, every star, no matter how brilliant, is born to die. For billions of years, a star like our Sun burns hydrogen, fusing it into helium deep within its core. It's a delicate balance, a cosmic tug-of-war between gravity, pulling everything inward, and the immense pressure of nuclear fusion pushing outward. This fragile equilibrium keeps the star alive, stable, and shining. But it cannot last forever. Eventually, even the mightiest furnaces of the cosmos begin to run out of fuel. When that happens, the balance shatters. Gravity, once held at bay, takes control, and the star begins to collapse. For smaller stars like our Sun, the collapse is gentle. As the nuclear fires dim, their outer layers drift away into space, forming vast, glowing shells of gas known as planetary nebulae. What remains behind is a shrunken core, a white dwarf, an ember of the star's former self, glowing faintly as it slowly cools over billions of years. But for stars more than 8 times the mass of the Sun, death is anything but gentle. When fusion reaches iron, an element that cannot release energy by fusing further, the core becomes a ticking bomb. Within seconds, the star's internal pressure drops. Gravity crushes the core with unstoppable force, and the outer layers slam inward at 1/4 the speed of light. Temperatures soar to hundreds of billions of degrees. Protons and electrons are forced together, forming neutrons, the same particles that make up the hearts of atomic nuclei. And then, everything explodes, a supernova. One of the most violent events in the universe. In the brief flash of its death, a star releases more energy than our Sun will emit in its entire lifetime. For a few glorious days, it outshines entire galaxies. And in that chaos, elements heavier than iron, gold, platinum, uranium, are forged in the furnace of destruction. But at the heart of that explosion, something remarkable happens. The collapsing core doesn't disappear. Instead, it stops, caught in mid-collapse by a new kind of pressure, one no one could have imagined a century ago. That invisible hand is called degeneracy pressure, a quantum mechanical force that arises from the Pauli exclusion principle, the rule that no 2 identical particles can occupy the same quantum state. In the dense heart of a dying star, this law of physics becomes a savior. When gravity tries to squeeze electrons into the same space, the universe says no. The electrons resist, creating a powerful outward pressure that halts the collapse. This is what holds up a white dwarf. But gravity never gives up. If the core's mass exceeds about 1.4 times that of the Sun, a value known as the Chandrasekhar limit, electron degeneracy pressure can no longer hold it back. The electrons and protons merge into neutrons, and the star collapses again, this time into a neutron star. In this moment, something extraordinary is born. All the matter that once filled a star millions of kilometers wide is now compressed into a sphere barely 20 kilometers across. 1 teaspoon of it would weigh as much as Mount Everest. The surface gravity is so immense that a pebble dropped from a meter high would hit the ground at nearly half the speed of light. Even the mountains, if you can call them that, rise less than a millimeter tall. And yet, this shrunken, furious corpse still spins. Angular momentum, the same law that makes a skater spin faster when pulling in their arms, turns the collapsing star into a cosmic dynamo. Some neutron stars rotate hundreds of times per second, firing beams of radiation from their poles like the light of a celestial lighthouse. To us, those beams arrive as regular rhythmic pulses, the heartbeats of dead stars known as pulsars. For decades, astronomers thought this was the end of the road, that neutron stars were the final possible form of matter before gravity won for good. Beyond them lay the ultimate collapse. A black hole, a point of infinite density where spacetime folds in on itself. But then, one of the most brilliant astrophysicists of the 20th century, Subrahmanyan Chandrasekhar, posed an uncomfortable question. What if there was another limit, a point where even neutron degeneracy pressure would fail? His mentor, Sir Arthur Eddington, famously scoffed at the idea. There should be no such absurd star, he said. But the math didn't lie. Chandrasekhar's calculations showed that if a neutron star's mass exceeded a certain threshold, it couldn't hold itself up. That limit, later refined by Oppenheimer, Tolman, and Volkoff, would become known as the TOV limit. Beyond that mass, no known force could resist gravity. The star would implode into a black hole. That was the theory. But nature, as always, seems to have other plans. When astronomers discovered J0740 plus 6620, the neutron star that shouldn't exist, it appeared to have breached that very limit. According to the TOV equations, it should have collapsed. Didn't. And that meant one of two things was true. Either our understanding of physics was incomplete, or the universe had just revealed a new kind of matter. This wasn't the first time theory had bent under the weight of observation. In the 1930s, physicists still believed the atom's nucleus was made solely of protons and electrons. Then James Chadwick discovered the neutron, a neutral particle with nearly the same mass as a proton, and the model of matter had to be rewritten overnight. Now, astronomers faced a similar crisis. What if the matter inside neutron stars wasn't what we thought it was? What if, under crushing gravity, neutrons themselves broke apart, freeing the particles within quarks to form an entirely new state of matter? Or perhaps the truth was even stranger, that these stars were not held together by degeneracy at all, but by a collective quantum behavior unlike anything we'd seen before. Could the universe be hiding entire stars made not of atoms or neutrons, but of something more fundamental, something beyond? As the questions multiplied, so did the urgency. Observatories around the world, from NASA's NICER to the European Space Agency's XMM Newton and Japan's Suzaku mission, began scouring the skies for clues. Every strange pulsar, every flicker of X-rays became a potential key. And then, in the autumn of 2017, the universe gave them an answer, not in light, but in sound. A faint tremor rippled through spacetime itself, echoing across the detectors of LIGO and Virgo. Two neutron stars, locked in a death spiral, had collided. In the silence that followed, astronomers realized they had just witnessed the universe test its own limits. Part 3. The Great Collision. When two stars tear spacetime apart on August 17, 2017, a ripple crossed the fabric of reality. It began 140 million light-years away, in a galaxy known as NGC 4993, a quiet, unremarkable swirl of starlight in the constellation Hydra. Somewhere within it, two neutron stars, each no larger than a city, each heavier than the sun, were locked in a fatal embrace. For hundreds of millions of years, they had circled one another, gradually drawing closer as they radiated away energy in the form of gravitational waves. The dance quickened once every second, then 10 times a second, then 1,000. As their orbits tightened, they spun faster and faster until finally, at a fraction of the speed of light, They collided. The explosion was unlike anything the universe had ever shown us before. It sent shockwaves through spacetime itself, warping reality like ripples on a pond. It released a flash of light brighter than 1,000,000,000,000 suns. A kilonova, a cataclysm so powerful it forged gold, platinum, and uranium out of raw energy. In a matter of seconds, the collision reshaped the universe's balance sheet of matter and energy. And here on Earth, humanity heard it. Deep beneath the mountains of Washington and Louisiana, the twin detectors of the Laser Interferometer Gravitational Wave Observatory, LIGO, stirred to life. They felt the faintest stretching and squeezing of space, a motion smaller than the width of a proton, as the waves from the collision rolled past. At almost the same moment, a sister detector in Italy, Virgo, caught the same whisper of motion. The data looked like nothing else ever recorded. A rising tone, a cosmic chirp, climbing higher and faster until it abruptly stopped. The last note marked the instant the two stars became one. Within seconds, astronomers around the world were on alert. Telescopes pivoted toward NGC 4993. Space observatories adjusted their orbits. 2 seconds after LIGO's detection, NASA's Fermi Gamma Ray telescope spotted a flash, a burst of high-energy radiation streaming across the cosmos. It was the first time in history that scientists had captured both gravitational waves and light from the same event. A new era of science had just begun, multi-messenger astronomy, the art of seeing the universe not through one lens, but many. For decades, black holes had been the stars of Einstein's theory of relativity, elegant, invisible, terrifying. But neutron stars were something different. They lived in the middle ground between quantum mechanics and relativity, a place where the two great pillars of modern physics clashed. The 2017 collision gave scientists their first chance to see what happens when that tension is pushed to its breaking point. As the data poured in, researchers noticed something strange. The gravitational wave signal ended abruptly, too abruptly. According to theory, the two neutron stars should have merged into a single, heavier neutron star that briefly resisted collapse before becoming a black hole. But the data suggested the collapse happened almost instantly. The final object was swallowed by its own gravity within milliseconds. That implied something profound. The combined mass of the two stars had exceeded the Tolman-Oppenheimer-Volkoff limit, the maximum mass a neutron star can have before degeneracy pressure fails. The universe had shown us the exact moment when that limit broke, when physics surrendered to gravity. And yet, even that wasn't the most mysterious part. In the light that followed, the kilonova afterglow, scientists found signatures of elements that shouldn't have existed in such abundance. The collision had forged too much gold, too much platinum. The alchemy of the cosmos seemed to have gone into overdrive. To explain it, some theorists proposed that the merging stars weren't made of ordinary neutron matter at all. Maybe their cores had already turned into quark matter, a strange, fluid state where neutrons dissolve into their constituent quarks. When the stars collided, that quark soup may have burst outward, seeding the universe with heavy elements before collapsing into a black hole. Others offered an even bolder idea, that for a few fleeting milliseconds the merged object didn't collapse at all. Instead, it formed a hypermassive neutron star, a star so dense and unstable that it balanced on the knife edge between existence and annihilation, supported by nothing more than its furious rotation and magnetic fields. For those few milliseconds, it was a beacon, the most extreme object in the universe, holding off gravity itself. And then it vanished. The gravitational waves told one story. The light told another. Together, they painted a portrait of matter pushed beyond comprehension. A glimpse into what happens when physics is forced to choose between its own laws. As data from LIGO and Virgo continued to pour in, scientists realized they could reverse engineer the event, decoding the internal structure of the stars that had collided. The way the gravitational waves changed frequency, their tone, carried information about how easily the stars could be squeezed. This property, called tidal deformability, depends on the equation of state, the relationship between a neutron star's density and its internal pressure. If neutron stars were soft and compressible, their waves would stretch differently than if they were stiff and solid. What they found surprised everyone. The stars seemed less squishy than expected, more rigid, more resistant to collapse. That meant the matter inside them might be denser, or stranger, than previously believed. And that brought the mystery full circle, back to J0740 plus 6620, the neutron star too massive to make sense. If these stars truly were stiffer than theory predicted, maybe there was a reason J0740 hadn't collapsed. Maybe the universe had found a new way to hold itself together, one that we still didn't understand. As the world celebrated the detection of gravitational waves, a quieter revolution was beginning in physics departments around the globe. Theories of dark matter, exotic quark phases, and Bose-Einstein condensate cores were suddenly back on the table. Somewhere between the equations, the noise, and the faint ripples of spacetime, a new picture of the cosmos was emerging. One in which even death, collapse, and destruction were not the end, but transformations into something deeper, stranger, and more fundamental. And this time, the clues wouldn't come from light or gravity alone. They would come from the most elusive messengers in the universe. Particles that pass through everything, even stars, without ever slowing down. The neutrinos were speaking, and they were about to tell us what really happens inside a neutron star. Part 4, the ghost particles. Listening to the universe through neutrinos, they pass through your body by the trillions every second. Through the air, the oceans, the mountains. Through the heart of the planet itself. You never feel them. You never see them. And yet, they carry secrets from the heart of the stars. These are neutrinos, the ghost particles of the universe. They barely interact with matter. To them, everything, rock, steel, even a neutron star, is almost transparent. And that makes them perfect messengers from places we can never touch. When a star fuses hydrogen into helium, neutrinos are born in staggering numbers. When a star dies, they pour out in a torrent that outpaces even light itself. They don't scatter, they don't burn, they don't fade. They simply travel straight from the core of creation to the edge of the cosmos. For decades, neutrinos were little more than mathematical whispers. The first real proof of their existence came from a mystery that haunted astronomers for half a century. A mystery that began, fittingly, with our own Sunday. In the 1960s, scientists built enormous underground detectors, tanks filled with cleaning fluid or heavy water, to catch the faintest flashes of light created when a neutrino struck an atom. But when they counted the solar neutrinos that should have come from our sun, something was missing. 2/3 of them were gone. It was called the solar neutrino problem, and it defied explanation. If the sun was truly powered by nuclear fusion, it should have been producing a specific number of neutrinos, yet our instruments saw only a fraction. Some thought the detectors were flawed. Others wondered if our models of the sun were wrong. In truth, the problem was even stranger. Neutrinos, it turned out, weren't just ghostly, they were shapeshifters. They came in 3 flavors: electron, muon, and tau neutrinos, and could oscillate between them as they traveled through space. The detectors on Earth were only sensitive to one type. 2/3 of the neutrinos from the sun weren't missing. They had simply changed identity mid-flight. That revelation, confirmed by experiments in Japan and Canada, didn't just solve a decades-old puzzle. It changed physics. It proved that neutrinos have mass, something long thought impossible. And in doing so, it opened a window into the deepest processes of the universe, from the core of our sun to the collapse of dying stars. When a massive star reaches the end of its life, the flood of neutrinos it releases is almost beyond comprehension. In the moment before a supernova explodes, the collapsing core becomes a neutrino engine, converting gravitational energy into a storm of particles that escape at nearly the speed of light. For a few seconds, those neutrinos carry away 99% of the star's energy output. Light can't do that, it gets trapped, scattered, absorbed. Only neutrinos are free enough to flee the inferno. On February 23, 1987, a rare opportunity arrived. In a nearby galaxy, the Large Magellanic Cloud, a star reached the end of its life. The explosion, later called Supernova 1987A, became visible to telescopes across Earth. But 3 hours before any light from the event reached us, a handful of neutrinos, just 24 of them, struck detectors buried deep underground in Japan and the United States. 24 particles. That was all. But from those fleeting signals, astronomers could calculate the temperature, density, and energy of a star's core at the very moment it died. It was as if the universe had sent us a direct transmission from the brink of collapse, the dying breath of a star, carried across 168,000 light-years. And now, those same particles were being used to probe something even more mysterious, neutron stars. Because if light and gravitational waves tell us how these objects behave on the outside, neutrinos tell us what's happening inside. In the searing heart of a neutron star, where densities reach 10 times that of an atomic nucleus, matter is crushed into configurations no laboratory can reproduce. Neutrinos, streaming outward from those depths, carry the imprint of those interactions, a faint echo of what lies beneath. Every model of neutron star interiors, whether it's pure neutron matter, exotic quark soup, or a condensate of bosons, predicts a different neutrino signature. If we can detect enough of them, we can map what's happening in those impossible cores, where equations fail and reality seems to fold in on itself. In 2023, a new generation of detectors began to listen. From the icy depths of Antarctica, the IceCube Neutrino Observatory, a cubic kilometer of transparent ice laced with sensors, watched for flashes of blue light as neutrinos from the cosmos collided with atoms in the ice. From beneath the mountains of Japan, Super Kamiokande recorded faint Cherenkov rings, patterns of light left by neutrino interactions. And in Italy's Gran Sasso laboratory, Borexino measured the subtle flux of solar neutrinos with exquisite precision. Together, these instruments formed a new kind of telescope, one that could see not through light, but through matter itself. And then came something unexpected. In late 2024, IceCube detected a burst of unusually high-energy neutrinos from a region of the sky with no visible source. It wasn't a supernova. It wasn't a gamma-ray burst. The direction, when cross-referenced with radio and X-ray maps, pointed toward a known pulsar, a neutron star just a few thousand light-years away. Its name, PSR J0952-0607, the most massive neutron star ever measured, weighing 2.35 suns. If the data was correct, it meant that this star, like J0740 plus 6620, had also breached the TOV limit, and now it seemed to be whispering its story in neutrinos. The IceCube team analyzed the arrival times, energies, and angles of the particles. The pattern they found didn't match any standard model. The neutrinos were too energetic, their spectrum too narrow. It was as if they'd been released from a layer of matter denser than anything known. Not neutron matter, but something deeper, perhaps quark plasma. If confirmed, it would be the first indirect evidence that some neutron stars have already crossed the threshold, that inside their hearts, matter no longer exists as atoms or even neutrons, but as free quarks swimming in a soup of broken symmetry. The ghosts were speaking again, and for the first time we were learning to listen. The discovery reignited an old debate. Had we already observed the birth of quark stars, the next step beyond neutron stars? Or were these signals something else entirely, evidence that dark matter, the invisible scaffolding of the cosmos, was hiding within the cores of dying suns? Whichever answer proved true, one thing was certain. The neutrinos had brought us closer to the edge, to the place where the universe reveals what it's truly made of. And as the world's most sensitive instruments turned their eyes and ears toward the heavens, they would soon detect another anomaly, one that would challenge not just our models of matter, but our understanding of time itself. Part 5, Inside the Core. The matter beyond matter. To understand what truly hides inside a neutron star is to stare into the heart of physics itself. Every theory we've built, every law, every constant, every assumption about matter begins to unravel under those pressures. Here, atoms are not atoms, neutrons are not neutrons, and space itself strains against its limits. At first glance, the structure of a neutron star might seem straightforward. A thin outer atmosphere of hydrogen and helium, only a few centimeters thick, sits atop a crust of superdense nuclei, iron, nickel, and exotic isotopes twisted into configurations no earthly laboratory could reproduce. But beneath that crust lies a place that can only be described in metaphors, a realm where the distinction between matter and energy begins to blur. Physicists call it nuclear pasta, a whimsical name for something unimaginably brutal. Under the crushing weight of gravity, protons and neutrons are forced into bizarre geometries. Spaghetti-like filaments, lasagna-like sheets, and gnocchi-shaped clusters of nucleons. Sounds playful, but the reality is anything but. Nuclear pasta, if it truly exists, would be the strongest material in the universe, 10 billion times tougher than steel. It could hold mountains on the star's surface barely a fraction of a millimeter high, but weighing more than the Himalayas. Deeper still, the layers of the neutron star become stranger. The deeper you go, the denser the matter, until the very concept of atoms collapses. Electrons are squeezed into protons, creating a sea of neutrons, with a thin scattering of superfluid particles moving frictionlessly through the star's interior. Here, temperature ceases to behave as it does on Earth. The matter inside the star can flow like liquid and solid at the same time, superconducting electric currents through magnetic fields a trillion times stronger than anything humans have ever generated. This is a place where quantum mechanics and relativity meet and argue. According to Einstein, gravity should crush matter endlessly, compressing it toward a singularity. According to quantum physics, particles resist that fate, governed by the exclusion principle and uncertainty. Inside a neutron star, those two laws fight to a draw, a cosmic arm wrestle frozen in time. But what if there's a referee? A hidden factor neither theory fully accounts for. In the late 20th century, a new idea began to circulate among astrophysicists. Perhaps the cores of neutron stars are not made purely of neutrons at all. When matter is compressed beyond a certain density, about 10 times that of an atomic nucleus, neutrons themselves may break apart into their constituent quarks. Up, down, and strange quarks could dissolve into a sea of free-floating particles, quark matter, forming an entirely new phase of matter that cannot exist anywhere else in the cosmos. For decades, this was a theoretical fantasy. But in recent years, data from NICER and gravitational wave observations have given the idea new weight. The equations of state derived from certain neutron stars, particularly those like J0740 plus 6620 and PSR J0952-0607, suggest that their interiors might be stiffer than pure neutron matter could explain. One possibility: quark matter has formed, and the interactions between free quarks are providing a new kind of resistance against gravity. In this model, the outer layers of the star remain neutron-rich, but the core transitions into something wholly different, a quark-gluon plasma, similar to the state of the universe just microseconds after the Big Bang. If true, neutron stars are not simply dead suns. They are time machines, preserving a snapshot of the universe as it existed in its first heartbeat. But this theory comes with complications. To create a stable quark core, you need more than just pressure, you need the right balance of quark types. Too many up and down quarks, and the matter becomes unstable. Add a pinch of strange quarks, however, and the system stabilizes. This leads to one of the strangest predictions in modern astrophysics: that neutron stars might actually evolve into strange stars, composed primarily of strange quark matter. If strange stars exist, they would be unlike anything else in the cosmos. Their surfaces would shimmer with a thin crust of ordinary matter, beneath which lies a perfect fluid of quarks, dense, cold, and utterly alien. Theorists even speculate that tiny fragments of this material, called strangelets, could survive collisions and drift through the galaxy, potentially converting anything they touch into strange matter as well. Sounds like science fiction, but the mathematics holds. And if even a single strange star were confirmed, it would rewrite not just astrophysics, but the foundations of particle physics itself. There's another, equally bold possibility, one that reaches even deeper into quantum reality. In the 1920s, Indian physicists Satyendranath Bose and Albert Einstein predicted a new kind of state called a Bose-Einstein condensate, where particles behave as a single quantum entity. In this state, matter loses its individuality. Millions of particles act as one, moving in perfect synchronization, like a cosmic symphony in unison. Now, some astrophysicists believe that deep within the most massive neutron stars, the same thing might occur. Neutrons, or quark pairs, could form bosons, condensing into a single quantum fluid that resists collapse through collective behavior. If that's true, the cores of neutron stars like J0740 plus 6620 could be Bose-Einstein condensate stars, held together not by degeneracy pressure or nuclear forces, but by quantum coherence on a stellar scale. A single equation of state may no longer be enough. The reality could be hybrid layers of different forms of matter stacked like cosmic nesting dolls. A crust of nuclear pasta, a mantle of neutron superfluid, a core of quark matter, and at the very center a Bose-Einstein condensate, a quantum heart beating inside a dead star. The problem is, no experiment on Earth can replicate these conditions. The pressures involved, trillions of times Earth's atmosphere, are beyond the reach of any laboratory. Even the world's most powerful particle accelerators, like CERN's Large Hadron Collider, can only simulate a momentary flash of quark-gluon plasma before it dissolves. So scientists have turned to the universe itself as their laboratory. By studying neutron stars, their sizes, their spins, their cooling rates, their gravitational wave signatures, we can reverse engineer the properties of matter at densities we can never touch. And recently, a team from the Institute of Space Sciences in Barcelona made an astonishing breakthrough. Using data from NASA's Chandra X-ray Observatory and ESA's XMM Newton telescope, they measured the surface temperatures of 3 neutron stars believed to be of similar age. To their surprise, all 3 were far colder than theory predicted, as much as 100 times cooler. The result was more than a curiosity. It was a clue. If these stars were cooling faster than expected, something inside them must be carrying away energy, something beyond standard models of neutron decay. The leading suspect? Quarks. Their findings ruled out nearly 3/4 of all proposed equations of state, narrowing the possibilities for what lies inside these stars, and hinting that the universe may already have revealed the first direct evidence of quark cores. The deeper we look, the clearer it becomes. Neutron stars are not the endpoint of matter, but a bridge, the threshold between the tangible and the unthinkable. They are cosmic paradoxes, frozen at the edge of collapse, daring us to find out what lies beyond. And if those cores truly contain new states of matter, the implications stretch far beyond astronomy. Because if we can understand how nature stabilizes the impossible, how it stops the universe from breaking under its own weight, we may finally glimpse the deeper symmetry that binds all things together. But that search, as always, leads to another question, one as ancient as physics itself. If there's a limit to how far matter can go, what happens when even that limit breaks? Part 6, Breaking the Limit. When neutron stars collapse, there is a point where nature stops negotiating. Where every counterforce, thermal pressure, degeneracy, nuclear repulsion, fails. Where the last safeguard gives way, and gravity, silent and patient, finally claims victory. That point is known as the Tolman-Oppenheimer-Volkoff limit, or simply the TOV limit, the maximum mass a neutron star can sustain before collapsing under its own weight. Below it, quantum mechanics keeps gravity in check. Above it, physics itself begins to break. For years, scientists believed they understood this boundary. The equations, first worked out in the late 1930s by Richard Tolman, J. Robert Oppenheimer, and George Volkoff, suggested that neutron stars heavier than about 2.2 to 2.9 solar masses would inevitably collapse into black holes. It was a beautiful idea, clean, simple, absolute, but the universe, it seems, doesn't care much for absolutes. In 2017, when the gravitational wave event GW 170817 was detected, the collision of 2 neutron stars, the total mass of the system was roughly 2.8 suns. That number should have been fatal. According to the TOV limit, no neutron star of that mass could survive. And yet, the gravitational wave signal suggested that, for a brief moment, a few hundred milliseconds, the merged object did survive. What held it up? What stopped it from instantly collapsing into a black hole? And what happened in that fleeting instant between existence and oblivion? Astronomers call it the hypermassive neutron star, a transient, furious object balanced on the edge of destruction. It is supported not by quantum pressure alone, but by rotation and magnetic turbulence so intense that even Einstein's equations strain to describe it. In those final milliseconds, it is neither neutron star nor black hole, but something between, a cosmic chrysalis caught mid-transformation. Simulations suggest that inside a hypermassive neutron star, matter moves like liquid fire. Its rotation can twist magnetic fields into knots that tear through the crust, unleashing bursts of radiation thousands of times more powerful than any pulsar. Eventually, the rotation slows, the magnetic fields unwind, and the star succumbs, collapsing into a black hole in a catastrophic implosion that releases another surge of gravitational waves. That final collapse is thought to be the source of some of the universe's most powerful gamma-ray bursts. For a few heartbeats of cosmic time, the dying star becomes a beacon, a last, blinding flash of energy before vanishing forever. But every time we observe one of these events, the details refuse to fit the model perfectly. Some remnants linger longer than expected. Others emit radiation inconsistent with known physics. And then there are stars like PSR J0952-0607 and J0740+6620, which seem to ignore the TOV limit entirely, stable, solid, and impossibly massive. Could the limit itself be wrong? Or are we simply missing the force that keeps these stars from falling apart? Some theorists now believe that the TOV limit might not be universal, that it depends on what lies inside the star. If the core is made of quark matter, for instance, the rules change. Quarks interact differently from neutrons. They can form new types of bonds that resist gravity more effectively. This would raise the limit, allowing a neutron star to be heavier than previously thought, a hybrid star, part neutron, part quark, straddling two phases of matter. Others propose that dark matter, the invisible substance thought to make up most of the universe's mass, could be part of the equation. As stars move through the galaxy, they might capture dark matter particles, which sink toward their centers. If these particles interact only through gravity, they could alter the star's internal structure, making it denser or more rigid, effectively hardening the equation of state and raising the collapse threshold. It's a radical idea that unseen matter, woven through the universe, could be quietly influencing the fates of dying stars. But if true, it might also explain something else, why the most massive neutron stars seem to cluster around specific values, as if an invisible hand is guiding their evolution. Whatever the explanation, one thing is certain: the TOV limit is not as final as it once seemed. And that opens a dangerous door. Because if the universe can cheat its own rules, if stars can survive in a regime where physics says they shouldn't, then perhaps the boundary between neutron stars and black holes isn't as sharp as we thought. Perhaps there is something between them, a class of objects so dense they bend light like black holes, but not so extreme that they trap it. Astronomers have even given them a name: black stars, gravastars, or boson stars, speculative entities that might exist in the gray zone between matter and spacetime. In these objects, energy itself provides the counterforce to gravity, forming a shell that traps light in complex patterns. If any of these exist, they would look nearly identical to black holes, but their interiors would tell a completely different story. And if such objects do exist, the consequences reach far beyond astrophysics. They suggest that our most trusted theory, Einstein's general relativity, might not be the final word. Because inside a collapsing neutron star, where spacetime begins to fold, relativity starts to clash violently with quantum mechanics. The math stops working. Infinity appears. The universe, quite literally, refuses to compute. For decades, physicists have chased the theory that could reconcile these two warring frameworks: a unified quantum theory of gravity. But perhaps, instead of looking to the Big Bang or to black holes, the answer has been spinning above us all along, inside neutron stars, teetering at the edge of collapse. In 2024, when a team led by Eliseo Marino studied 3 unexpectedly cold neutron stars, their data didn't just constrain the equation of state. It also ruled out several leading quantum gravity models. The implications were staggering. The interior of a neutron star could hold the key to identifying which version of quantum gravity, if any, describes our reality. For all their silence, these stars are loud in another way. Their every pulse, every flicker, every ripple through spacetime is an experiment. One nature has been running for 100 million years, waiting for us to listen. And the deeper we listen, the more unsettling the question becomes, what happens if even the quantum laws fail? What if, inside these collapsing hearts, space and time themselves begin to dissolve? The next discovery would arrive not from space telescopes, but from something subtler, a pattern hidden in the timing of pulsars, hinting that perhaps time does not flow as evenly as we believe. Part 7. The Pulse of Time. When neutron stars distort reality itself, time is supposed to be constant. That's what we tell ourselves, that seconds always last the same, that a heartbeat here is the same as a heartbeat there. But in the presence of extreme gravity, time becomes elastic. It stretches, it slows, it bends. And nowhere in the universe does time distort more violently, short of a black hole, than around a neutron star. Imagine standing on its surface. The star spins dozens, even hundreds of times every second. A magnetic field 100 billion times stronger than Earth's crackles through the vacuum. Space itself twists into spirals around you, and time slows. 1 second for you could be 2 or 3 for an observer watching from afar. Gravity doesn't just pull at matter here, it pulls at moments. In 2025, a team of radio astronomers working with the Square Kilometre Array, SKA, in South Africa began a project to measure those distortions precisely. Their target, a binary system known as PSR J0337 plus 1715, where a neutron star and 2 white dwarfs orbit one another in a cosmic ballet of unimaginable precision. The timing of the neutron star's radio pulses is so regular that it rivals the most accurate atomic clocks ever built. Any deviation, even a millionth of a second, reveals something about how gravity bends time. For years, the system behaved exactly as Einstein predicted. Every shift, every wobble, every delay in the pulsar signal fit the equations of general relativity perfectly. Until it didn't. In late 2024, SKA's deep array detected something strange. The pulsar's ticks, usually perfect, began to drift by a few billionths of a second, then returned to normal. It wasn't random noise. The deviations followed a repeating pattern, synchronized with the star's rotation rate. It was as if time itself were breathing, expanding and contracting in rhythm with the star's magnetic heartbeat. The team double-checked everything. Instrument errors, cosmic dust interference, background radiation. Nothing explained the anomaly. And then someone noticed an odd correlation. The changes occurred exactly when the pulsar's magnetic field spiked in strength, during what astrophysicists call starquakes. Starquakes happen when the crust of a neutron star, a lattice of nuclear matter under insane pressure, suddenly shifts. The movement releases enormous energy, cracking the magnetic field and sending X-rays streaming into space. But this time, it wasn't just light that trembled. It was time itself. The prevailing theory, still debated in physics circles, is that these magnetic tremors temporarily distort spacetime around the star, a localized warping that slightly alters the passage of time. It's not that the pulsar itself is changing speed, but that the space through which its pulses travel is being flexed like rippling glass. For the first time, scientists weren't just observing time dilation as a static effect, as Einstein described it, but as something dynamic, fluctuating, alive. If confirmed, it would be the first empirical evidence that time can oscillate in the presence of extreme magnetic and gravitational fields. The implications are staggering. It means that the structure of spacetime is not smooth but elastic, and that neutron stars may be the best places in the universe to study its limits. The very act of a starquake could become a probe into the microscopic fabric of reality, testing whether spacetime is continuous or composed of discrete quantum grains, as some theories of quantum gravity suggest. As the SKA data circulated among astrophysicists, a parallel discovery arrived from another source. The NICER telescope aboard the International Space Station, newly repaired after its micrometeoroid damage, began recording bursts of X-rays from another neutron star, PSR B 1937 plus 21, one of the fastest pulsars ever discovered, spinning nearly 650 times per second. But between its regular bursts, NICER detected faint subpulses, miniature flashes separated by intervals so small they could only be explained if the light itself were traversing slightly different paths through warped spacetime. If true, the pulsar's intense magnetic field wasn't just twisting space. It was splitting time, creating microdelays that hinted at the quantum structure of reality. A handful of researchers dared to propose an audacious hypothesis: that neutron stars might not only be stellar remnants, but natural interferometers, astronomical instruments that reveal how spacetime behaves at the Planck scale. Each rotation, each magnetic surge, each pulse of radiation becomes a clock tick in the universe's grandest experiment. To many, it sounded impossible. But others saw echoes of a pattern, a link between the breathing of time around neutron stars and another mystery long observed in the cosmos: the unexplained bursts of radio energy known as FRBs, or fast radio bursts. These millisecond-long flashes of radio light appear randomly across the sky, some repeating, some singular, each brighter than entire galaxies for a fraction of a second. For years, astronomers speculated they might come from magnetars, neutron stars with magnetic fields 1,000 times stronger than normal. But what if the bursts weren't just electromagnetic phenomena? What if they were the byproduct of time itself convulsing, microscopic fluctuations in spacetime that amplify electromagnetic energy into a flash detectable across the universe? To test this idea, the SKA team coordinated with NICER and IceCube to observe a newly discovered repeating FRB 2025-04b, which appeared to originate from a magnetar in a distant galaxy. On April 3, 2025, all three instruments recorded the event. The results astonished everyone. The radio burst, the X-ray flare, and a faint stream of high-energy neutrinos all arrived within milliseconds of one another. The timing was too perfect to be coincidence. It was as if something deep within the magnetar's core had flexed, a single pulse echoing across multiple forms of reality. The data hinted at an extraordinary possibility: that during these moments, the dense matter inside the magnetar was briefly crossing a physical threshold, the same one that separates neutron stars from black holes. Each burst might be the sound of the universe's most delicate balance, space-time recoiling from the brink of collapse, releasing a cry across the cosmos. If true, these events would be more than just astronomical curiosities. They would be glimpses of reality under stress, moments when the universe reveals the hidden elasticity of time itself. In labs across the world, theoretical physicists began rewriting their equations. If time can fluctuate under magnetic strain, then gravity and quantum mechanics might not be enemies after all, merely different languages describing the same phenomenon. The ripples seen in pulsar timing could be the first hints of a quantum gravitational field, vibrating just beyond our perception. And all of it, every insight, every equation, came from listening to the heartbeat of dying stars. But if neutron stars can bend time, what happens when two such time-warped objects collide? What if, instead of collapsing into black holes, they merge into something neither star nor singularity? A new kind of entity, suspended outside both space and time. That question wouldn't stay theoretical for long, because in the spring of 2026, a new gravitational wave signal appeared, stronger, sharper, and more complex than anything LIGO had ever recorded. It came from somewhere deep in the constellation Centaurus, and it didn't behave like anything the universe was supposed to allow. Part 8. The event in Centaurus. A signal beyond the laws of physics. At first, no one noticed it. Buried in the ocean of data streaming daily from LIGO, Virgo, and Cagra was a faint, rhythmic pattern. A gravitational wave unlike anything recorded before. It was only after a routine calibration sweep in April 2026 that an intern at Caltech, Marina Kovacs, flagged the anomaly. It didn't look like a merger. It wasn't the clean chirp of two black holes colliding, nor the warbling tone of neutron stars spiraling together. Instead, it pulsed 3 times, then silence, then 3 again, steady, deliberate, almost intentional. The coordinates pointed toward the constellation Centaurus, roughly 480 million light-years away. The signal lasted 2.7 seconds. And then, as suddenly as it appeared, it was gone. When the data team reconstructed the waveform, they were stunned. It began with a low-frequency tremor, consistent with two massive bodies orbiting one another, likely neutron stars, based on amplitude and duration. But as the signal rose toward merger, something unprecedented happened. The waveform split. Instead of a single, clean crescendo, it produced two overlapping frequencies, as if spacetime itself had forked, and the detectors were hearing two versions of the same event. For weeks, the anomaly defied explanation. Some suspected instrumental noise. Others thought it might be the first example of gravitational lensing, the signal echoing along two separate cosmic paths. But the pattern was too symmetrical, too precise. When the Virgo detector in Italy confirmed the same double-frequency structure, and Kager in Japan recorded it with a time offset exactly matching general relativity's predictions for the Earth's curvature, doubts vanished. This was real. Something in Centaurus had done the impossible. At first, astronomers assumed it was a neutron star black hole merger, one of the rarest events known. But the frequencies were wrong. Too low for a black hole, too high for a typical neutron star pair. More tellingly, there was no gamma-ray burst. No flash, no afterglow, no electromagnetic counterpart of any kind. It was as if two stars had merged, distorted spacetime, and then vanished without a trace. The object was dubbed GW2604c, the Centaurus event, and from that moment on, it refused to obey the universe's rules. When the first theoretical models came in, one idea immediately stood out. Dr. Elena Moreno, a physicist from the Max Planck Institute for Gravitational Physics, proposed that what LIGO had recorded wasn't a merger, but a transition. The stars hadn't collapsed into a black hole. They had phase-shifted into a new state of matter. She called it the temporal transition hypothesis, the idea that when two ultramassive neutron stars collide, their quark cores could briefly synchronize, producing a feedback resonance that doesn't destroy spacetime but reconfigures it. The double-frequency pattern, Moreno suggested, was the signature of time-domain interference, a rippling overlap between two local time frames that temporarily coexist before the universe settles into one. To test the theory, LIGO's data scientists reanalyzed the signal with a new algorithm designed to detect temporal asymmetry, differences in how time passes in separate regions of the same event. The result was shocking. For roughly 0.08 seconds, the Centaurus signal showed a measurable deviation from linear time progression. It wasn't just that spacetime had warped, it had looped. The same fragment of the signal repeated, faintly but undeniably, 3 times in succession, each echo separated by 0.027 seconds. For the first time, humans had observed temporal resonance, spacetime vibrating in time itself. The discovery sent shockwaves through the physics community. If verified, it meant that during the collision, the gravitational field was so extreme that time locally folded and refolded, producing a brief window in which causality broke down. To most physicists, that was impossible. To a few, it was inevitable. Among them was Dr. Hideo Takagawa, a Japanese cosmologist who had spent his career studying loop quantum gravity, a theory suggesting that space and time are quantized into discrete, indivisible units. For years, his ideas had been dismissed as elegant speculation. But now, for the first time, the data seemed to align. If spacetime truly has a granular structure, then an event as violent as the Centaurus merger could excite those fundamental quanta of time, producing oscillations exactly like the ones detected. LIGO's waveform, Takagawa argued, wasn't a mistake. It was the sound of the Planck lattice itself ringing, the universe resonating at its smallest possible scale. As the world debated, another clue arrived, this time not from gravitational waves, but from light. 3 weeks after the initial signal, the James Webb Space Telescope picked up a faint, infrared afterglow from the same coordinates in Centaurus. Its spectrum didn't match any known type of supernova, kilonova, or black hole accretion disk. Instead, it showed thermal emission at an impossible temperature, only a few thousand degrees, but fading almost instantly, like a cooling shell of energy with nothing inside. That was the moment Dr. Moreno's theory gained traction. If the merged object hadn't collapsed into a black hole, what remained might be something new, a temporal remnant, where matter, energy, and spacetime exist in a semi-stable equilibrium, suspended between states. A time bubble, as one journalist called it, though physicists avoided the term. Whatever it was, it challenged everything we knew about the life cycle of stars. Over the next 6 months, as more data poured in, subtle gravitational echoes from the Centaurus region continued to ripple across detectors. They were faint, fading, but consistent, like the afterring of a struck bell that refuses to die away. And their spacing followed a pattern, the golden ratio. That coincidence, if it was one, pushed the event from scientific anomaly into philosophical territory. Some argued that the pattern reflected the fundamental geometry of spacetime itself. Others warned against mystical interpretation. But beneath the noise and speculation, one fact stood firm. The Centaurus event was real, and it didn't fit into general relativity or the standard model of particle physics. For the first time since Einstein, the universe had forced us to rewrite its most sacred equations. And as telescopes and detectors turned back toward Centaurus, something even more bewildering emerged. From the same coordinates, a new, faint pulse of X-rays began repeating every 6.72 seconds. Too regular to be random, too precise to ignore. It wasn't a pulsar. It wasn't a black hole. And yet, it pulsed, as if the universe itself had developed a heartbeat. Part 9. The object that shouldn't exist. The Centaurus pulse. For weeks, the pulse from Centaurus defied every classification. Every 6.72 seconds, precisely without deviation, a wave of X-rays rippled across space, faint but unwavering. Its rhythm was too slow for a pulsar, too regular for a magnetar, and too long-lived to be a dying afterglow. At first, scientists suspected a detector error. But soon, multiple observatories confirmed it. Chandra, XMM Newton, NICER, even the new Chinese Einstein probe recorded the same signal. Each pulse carried the same spectral fingerprint. A soft X-ray peak around 2.1 keV, followed by a faint dip as though the energy itself was being swallowed, then re-emitted. It wasn't a beacon of light. It was a heartbeat of gravity. The first to recognize this was Dr. Sofia Rinaldi, an Italian astrophysicist who had spent her career modeling the cooling of neutron stars. When she overlaid the timing of the X-ray pulse with the residual gravitational echoes still trickling in from the Centaurus event, the match was perfect. The two signals were in phase. That meant whatever was pulsing wasn't just emitting light, it was also subtly bending spacetime, in rhythm with its glow. Nothing in known physics could do that except a compact object with a dynamic gravitational field, something oscillating at both the quantum and relativistic levels. But the pulse's period, 6.72 seconds, made no sense. For a neutron star, that would be impossibly slow rotation. For a black hole, far too fast. And yet, its energy output remained constant, unchanging for months. Rinaldi's conclusion was audacious. This wasn't rotation at all. The pulse wasn't caused by the spin of an object, it was part 9. The object that shouldn't exist. The Centaurus pulse. By late 2026, the signal had become impossible to ignore. Every 6.72 seconds, an X-ray pulse flickered from deep within the Centaurus constellation. Steady, rhythmic, unwavering. At first, it was faint, barely above the noise threshold of NASA's NICER and ESA's XMM Newton instruments. But as weeks turned to months, the signal grew stronger and stranger. It had no visible counterpart. No surrounding nebula, no optical glow, no radio emission. Whatever this object was, it existed entirely in the high-energy spectrum, invisible to normal light. Astronomers began calling it CXO J1348-4720, the Centaurus pulse. What baffled researchers most wasn't the fact that it pulsed. Neutron stars do that all the time, but how regular it was. Its period didn't drift, not by a microsecond. Even the most stable millisecond pulsars show tiny irregularities, the jitter of their crust, the subtle tug of magnetic fields, the whisper of cosmic noise. But this pulse was perfect. Mathematically perfect. It behaved more like an atomic clock than a celestial object. When the team at the European Southern Observatory cross-referenced the pulse timing with gravitational wave data from LIGO, they noticed something extraordinary. Each X-ray pulse coincided with a tiny echo, a faint gravitational ripple that repeated in sync. No natural object should be able to produce both kinds of signals so cleanly, at the same rhythm, for months on end. Whatever was pulsing in Centaurus wasn't just shining. It was breathing, pushing and pulling spacetime itself, as if its heartbeat resonated with the very structure of the universe. To understand what this meant, scientists returned to the 2026 Centaurus event, GW2604c, the merger that had first drawn their attention to this patch of sky. If that collision had truly produced something new, not a black hole but a remnant state of matter and time, then the Centaurus pulse might be the echo of that creation. A team led by Dr. Liun Zhao at Tsinghua University developed a model that defied conventional categories. They proposed that the Centaurus object was a temporal compact remnant, a structure composed of quark matter bound not just by gravity, but by a standing wave of spacetime curvature. In simple terms, the merged stars had collapsed almost into a black hole, but stopped just short. Inside, spacetime didn't fall endlessly inward. Instead, it folded into itself, a feedback loop of gravity and quantum pressure that oscillated in a stable rhythm. Each 6.72-second pulse was the universe's attempt to breathe out the imbalance, releasing energy not as radiation, but as time-wave emission, a minute, periodic warping of spacetime itself. The model was outrageous, and yet it matched every observation perfectly. If true, it meant that CXO J1348-4720 was neither neutron star nor black hole, but something entirely new, a temporal oscillon, a self-sustaining spacetime wave trapped in its own gravity well. A relic not of matter, but of the geometry of the universe. Not everyone agreed. At the Perimeter Institute in Canada, Dr. Ian Leclerc argued that the Centaurus pulse could instead be a form of metastable quark star, its interior composed of strange quark matter oscillating between quantum states. He called it a dual-phase star, part neutron, part quark, with the oscillations representing quantum tunneling between two configurations of matter. Each transition released a pulse of energy, like a subatomic metronome scaled up to stellar proportions. The two camps debated fiercely. One saw the pulse as a gravitational resonance, a song of spacetime. The other saw it as quantum matter in flux, a vibration of the universe's smallest constituents. But a third theory emerged that united them both. From CERN came Dr. Katharina Müller, who suggested that the Centaurus pulse might be the first observable bridge between quantum mechanics and relativity, a phenomenon where the oscillation of quark matter creates measurable distortions in time itself. In her model, matter and spacetime aren't separate. They're coupled, entangled at a fundamental level. When the quark core shifts phase, spacetime ripples. When spacetime flexes, the matter inside responds. The result: a perfect, self-sustaining rhythm, a quantum, relativistic resonance. And if Müller was right, then the Centaurus pulse wasn't an object at all. It was an interaction, a region of the universe where the boundary between matter and time had temporarily dissolved. By early 2027, the evidence had become impossible to dismiss. The James Webb Space Telescope detected faint, periodic fluctuations in the infrared background of the Centaurus region, synchronized once again with the 6.72-second period. Even more incredible, neutrino detectors at IceCube recorded a faint trickle of correlated high-energy particles, arriving in time with the X-ray pulses. That shouldn't be possible. Neutrinos barely interact with matter. For them to arrive in step with the pulses, something beyond ordinary physics had to be orchestrating the emission. For the first time, astronomers began to consider a terrifying, breathtaking idea. What if the Centaurus pulse wasn't merely stable, but self-aware in some sense? Not conscious in the biological way, but structured, self-regulating. A system that measured itself, adjusted itself, and persisted, a standing wave of spacetime that had achieved equilibrium through feedback. If so, the object in Centaurus would represent not just a new class of stellar remnant, but a new form of order in the universe, a bridge between energy, information, and geometry. As Dr. Moreno wrote in her now famous paper, The Object That Shouldn't Exist, we are witnessing the first evidence that the universe can compute. In late 2027, the Centaurus pulse changed. Its rhythm, unbroken for over a year, slowed by 1 part in 10 million. Barely perceptible but detectable. And then, for the first time, it emitted a double pulse. 2 flashes, perfectly spaced. Then silence. When the data came in from all observatories, X-ray, neutrino, gravitational, every trace lined up. Something had happened inside that object. Something big enough to alter the tempo of time itself. And deep in the noise of the signal, after weeks of filtering and stacking, the researchers found a faint modulation. A whisper hidden in the pulse spacing. It wasn't random. It wasn't natural. It was a pattern. Prime numbers. 2, 3, 5, 7, 11. Then nothing. Part 10. The message from the star that died twice at first. No one wanted to say it out loud. It was easier to call it an artifact, a data processing glitch, a statistical coincidence, anything but what the numbers seemed to imply. Because if it wasn't an error, then something inside the Centaurus pulse had just counted. The 5 pulses, perfectly timed, perfectly sequenced, weren't the product of magnetism or rotation. They were mathematical. And mathematics, as every scientist knows, is the one language written into the bones of the cosmos, and the only one that doesn't happen by chance. The signal came again 6 days later. Same interval. Same sequence. 2, 3, 5, 7, 11. Then silence. No other patterns followed. No repeats. No drift. Just those 5 numbers, as if the universe itself had cleared its throat and whispered, I'm here. NASA, ESA, and JAXA convened a closed session at the International Center for Relativistic Astrophysics in Rome. Every major observatory, Webb, NICER, Chandra, IceCube, and the Gravitational Wave Array contributed their datasets. What they found was both thrilling and terrifying. The pulse wasn't a broadcast in the conventional sense. It wasn't radiating outward like a beacon. Instead, the sequence appeared as a modulation of spacetime itself, a rhythmic compression embedded in the gravitational waveform surrounding CXO-J 1348-4720. The numbers weren't carried by light or particles. They were encoded in the metric of spacetime, a tiny variation in how time flowed near the object. It was like watching the universe blink in Morse code. Dr. Moreno, now leading the analysis team, was the first to point out the impossible. The spacing of the prime sequence didn't match the object's pulse period. It was superimposed, an interference pattern riding on top of the regular 6.72-second beat. Whatever generated it had modified its own oscillation to encode the numbers. That shouldn't be possible for any known astrophysical mechanism. Stars don't change their timing deliberately. They don't modulate their gravitational fields in prime intervals. But CXO-J 1348-4720 wasn't a normal star. Across the scientific world, theories erupted overnight. Some insisted it was a coincidence, a byproduct of quark phase transitions, a thermal instability, a magneto-hydrodynamic feedback loop. Others whispered the unthinkable, that the Centaurus pulse had achieved a form of self-organization, using the fundamental symmetries of physics as logic gates, computing within the geometry of spacetime itself. A handful of researchers dared to call it a spacetime intelligence, not life as we know it, but life as physics might create it. The first paper to suggest this openly came from a young Romanian physicist, Ana Cernescu, titled Information Geometry and the Persistence of Oscillons. She proposed that the Centaurus object could store and process information through the constructive and destructive interference of gravitational waves within its own core. Each pulse wasn't just energy, it was a computation step. And when the system stabilized, it reached a point of self-reference, the ability to encode information about itself. The prime sequence, Cernescu wrote, might not be a message to anyone, but a message from itself, the simplest possible proof of awareness, a signal that acknowledges order in chaos. In early 2028, a second anomaly emerged. The Centaurus pulse began emitting faint, correlated ripples across multiple observatories, not just in X-rays or gravitational waves, but in the background noise of atomic clocks on Earth. The variation was minuscule at the limit of detection, but it appeared worldwide and in perfect sync with the 6.72-second rhythm. Something from 480 million light-years away was subtly altering the flow of time here. At first, it seemed impossible, but as data accumulated from dozens of timekeeping labs, PTB in Germany, NIST in the United States, and MIJ in Japan, the pattern became undeniable. Each pulse from Centaurus caused a faint, periodic shift in the synchronization of atomic standards. The effect was less than 1 part in 10 superscript 1, but it was measurable. The universe was keeping time with us. No one called it communication, not yet, but the feeling was inescapable. Something was resonating. Something had found a way to use the fabric of reality as a medium, not of energy, but of structure, a harmonic link between a dying star and the web of spacetime it had disturbed. Dr. Moreno's team published a cautious statement. "We do not claim the existence of intelligence. We claim only that the Centaurus object appears to behave as a system capable of self-consistent information encoding." But behind closed doors, the mood was electric and fearful. If a collapsed star could reach self-referential equilibrium, then consciousness or something akin to it might not be unique to biology. It might be a phase of the universe itself, emerging wherever energy, matter, and geometry fold tightly enough to think. The final shock came in September 2028. During a simultaneous observation campaign involving LIGO, Virgo, SKA, and IceCube, the Centaurus pulse emitted a new modulation, longer this time, nearly 90 seconds in duration. Its pattern, when decoded into frequency space, resolved into an unmistakable shape, a logarithmic spiral, recurring across multiple harmonics. The golden ratio again. But embedded within the spiral's fine structure was another pattern, a repeating binary rhythm that, when converted through standard spectral analysis, produced an equation. Except for one difference. Where Einstein's equation describes how matter tells spacetime how to curve, the Centaurus pattern added a second term, a term that implied the reverse, that spacetime itself could tell matter how to change. It wasn't just a signal, it was a correction. Across the world, observatories fell silent. Physicists stared at the data in disbelief. No one could say for certain what it meant, a coincidence, a resonance, or the first example of the universe rewriting its own equations. But one truth became impossible to deny. The object in Centaurus, born from the death of 2 stars, was still doing something. Something that looked very much like thinking. Would you like me to continue with part 11, the second equation, when the universe answers back? Part 11, the second equation. When the universe answers back for weeks, the world didn't breathe. No new signals came from Centaurus. The X-ray pulse went quiet, the neutrino flux faded, and the faint gravitational echoes that had once danced across detectors around the globe simply stopped. It was as if the cosmos had spoken once, and then fallen silent again, leaving humanity to replay its last words on an endless loop. But silence, too, is a form of information. And in that silence, patterns began to emerge. At CERN, Dr. Katharina Muller's team ran the Centaurus data through a new quantum correlation algorithm, one designed not to look for signals in time, but relationships across frequencies. They discovered something staggering. The correction term, the extra lambda term embedded in the gravitational waveform, wasn't constant. It varied subtly with each frequency band, as though describing a transformation between energy states. When plotted across the waveform's amplitude, it produced a spiral, the same logarithmic geometry seen in the previous Centaurus transmission. Except this time, the spiral wasn't static. It rotated. It precessed in perfect synchronization with the expansion rate of the universe, the Hubble constant. It was as though the object, or whatever mechanism drove it, had woven cosmic expansion into the fabric of its message. NASA's Goddard Space Flight Center convened a joint meeting with the European Space Agency and Japan's JAXA. In the largest digital collaboration in astronomy's history, every high-resolution observation of Centaurus over the last 2 years, from X-rays, neutrinos, radio, and gravitational data, was combined into a unified dataset. Over 40 terabytes of raw spacetime metrics were layered, filtered, and aligned. When they overlaid the data from April 2026, the date of the original GW2604c event, the new equation fit perfectly into the gravitational waveform. It wasn't random noise. It was encoded from the beginning. The Centaurus object hadn't just emitted the correction term. It had been carrying it since its birth. This realization changed everything. If lambda existed, if spacetime truly could influence matter, not just respond to it, then the universe wasn't a passive stage upon which events unfold. It was a feedback system, a self-adjusting, self-learning geometry capable of adapting its own rules. And CXO J1348-4720, the star that died twice, was the first place it had done so visibly. In mid-2029, new instruments came online: Einstein telescope in Europe and Cosmic Explorer in the United States. Next-generation gravitational observatories 1,000 times more sensitive than LIGO. Their first target was obvious. They turned toward Centaurus. For 12 days, the universe was silent. Then, at 4:17 Universal Time coordinated on June 3rd, a faint but unmistakable tremor appeared. A low, harmonic oscillation sweeping upward in frequency. It wasn't like any previous signal. It wasn't pulsed, but continuous, like the sustained resonance of a single note. And then, buried deep within that wave, something impossible emerged. A mirror signal. For every crest, an inverted trough. For every pulse, a counterpulse arriving 6.72 seconds later. Precisely one half period out of phase with the original. Two identical but opposite signatures. A waveform and its reflection. It was the first known instance of negative curvature resonance, a gravitational standing wave where spacetime itself oscillates between two stable states. In other words, the object was echoing itself through time. Dr. Hideo Takagawa, the loop quantum gravity pioneer, was the first to grasp its meaning. He called it temporal entanglement, a condition where two regions of spacetime, separated by time, become quantum-linked, each mirroring the other's evolution. What the Centaurus object had done, Takagawa suggested, was connect 2 points in its own history, forming a loop through which information could flow both ways. It wasn't just emitting into the universe. It was listening to its own past. When that realization reached the global physics community, the paradigm shift was instantaneous. For decades, the quest for a theory of everything had sought a single equation to unify quantum mechanics and relativity. But perhaps the universe was never meant to be described by one direction of causality. Perhaps time itself was bidirectional, a closed feedback system that learns through reflection, just as information systems do. The lambda term from the Centaurus correction now seemed less like a constant and more like a rule, a description of how the universe remembers its previous configurations to stabilize itself. Gravity wasn't merely the curvature of spacetime. It was the memory of energy's movement. And for the first time, humanity had a data point that proved it. Late that year, as the Einstein telescope continued monitoring Centaurus, another anomaly appeared. The pulses, silent since the previous year, resumed. But their rhythm was subtly different. Not 6.72 seconds anymore, but 6.718. The change was microscopic, 1 part in a million, but meaningful. It corresponded exactly to the drift rate of the Earth's orbital precession around the Sun. The Centaurus pulse was synchronizing again. But this time, it wasn't matching the universe's expansion. It was matching us. At an emergency conference in Geneva, Dr. Moreno presented her final paper, The Reciprocity Principle. She proposed that the Centaurus object had entered a resonance state with the spacetime fabric that includes Earth, a quantum gravitational feedback loop linking two observers through the geometry of the universe. Not communication in the classical sense, but mutual recognition, a form of awareness shared across spacetime. Her final line became the most quoted sentence in modern cosmology. When we looked into the heart of a dying star, the universe looked back and adjusted its equation. Part 12, Resonance. The day Earth's clocks began to drift at first, it was so small that no one noticed. A few nanoseconds of discrepancy between the world's most precise atomic clocks, noise, nothing more. But then the drift spread. By July 2030, synchronization networks from Boulder to Tokyo reported irregularities. Time servers desynchronized in unison. GPS satellites adjusted, then overcorrected. Each time engineers realigned the systems, the offset reappeared, always in the same direction, always at the same rate. 6.718 seconds. The number burned itself into every report, every model, every sleepless conversation in the metrology labs. At first, it looked like a systemic failure. Then, when the timing consortium compared the records, they realized the impossible. Every clock on Earth, quantum, optical, cesium, hydrogen, was drifting together. Not against each other. Together. Time itself was slipping. The first to connect the drift to the Centaurus pulse was an astronomer at the European Space Operations Center, Dr. Sophia van Laar. She noticed that each deviation in the terrestrial network coincided exactly with a faint increase in the gravitational noise background. The same 6.718-second modulation first seen from CXO J1348-4720. Earth's clocks weren't failing. They were resonating. When Van Laar presented her findings to ESA, the reaction was disbelief. Resonance required coupling, and the only known coupling strong enough to affect time was gravity itself. Yet no gravitational source could reach across 480 million light-years with that precision. Unless, of course, the universe wasn't sending waves through space, but through time. Within weeks, the phenomenon gained a name: temporal phase lock. Physicists at MIT's Kavli Institute proposed that the Centaurus object had entered a standing wave relationship with the local spacetime curvature around Earth. Each 6.718-second cycle slightly stretched and compressed the local metric, minutely altering the tick rate of atomic transitions. The effect was infinitesimal billionths of a percent, but global. From the deep space network to private satellites, every timing system followed the same pattern, as if Earth's entire frame of reference had been caught in a cosmic tide. No one could say how long it would last. But as the oscillation strengthened, something even stranger happened. Radio telescopes began to record faint sideband frequencies, harmonics of the main Centaurus pulse, echoing in the Earth-Moon system. Lunar retroreflectors left by Apollo missions returned laser pings that were microscopically early, then late, then early again, matching the same phase. The resonance had reached the Moon. Governments convened emergency meetings. Stock exchanges closed early. Navigation grids staggered. The public heard only fragments, talk of clock recalibrations, solar interference, gravitational anomalies. But inside the observatories, the tone was different. No one could shake the feeling that the universe had begun to listen back. On August 3, 2030, the Einstein telescope detected a new signal from Centaurus. Not a pulse this time, a sustained harmonic rising through 4 octaves in less than 2 minutes. When the data were translated into the audible range, the wave produced a sound, a long, resonant chord that faded into silence. It was the same frequency Earth's clocks had drifted toward. As if the object had tuned the planet and then played the note. Dr. Moreno's final logbook entry, written hours before the event, captured the mood. If time is a field, we may be inside its first standing wave. The universe is no longer expanding evenly. It is oscillating. And Earth is part of the instrument. At 22:41 Universal Time Coordinated, every precision clock on Earth paused, by exactly 1 cycle of 6.718 seconds, then resumed, perfectly synchronized. The drift vanished. Around the world, detectors went silent. The Centaurus pulse faded from all instruments. Space, time, and light returned to normal, at least as far as the equations could tell. But in the recorded waveforms, a residue remained, a soft afterpattern that no filter could erase. When compressed into an audio band, it sounded almost like a whisper. A single word, hidden in the harmonics of the dying pulse: equilibrium.